Yeah, it's loud and clear.
Yeah, thank you. Those people who don't know me, myself, I am Jobi
Yeah,
Jacob.
yeah. Again, you are quite audible. Just a few minutes before we actually start off, Jobi,
Yeah,
uh, we'll wait for 5 more minutes for more people to
yeah, yeah.
join, and then we can formally get going. I will
Sure,
introduce you,
sure.
and then you can take over. Yeah.
Okay, okay, fine, fine. Yeah.
We have 31 participants. Time is 3:04 here in India. Okay, it's 3:05. So maybe we can start off with the 32 participants. Good evening and welcome to all participants to this webinar series. A warm welcome to Mr. Jobi Jacob Joseph, who is our speaker today. This is the final day of the electrical safety webinar talk series that we started from 27th June 2023. The webinar is jointly conducted by HSE Forum of National Safety Council Kerala chapter along with the Department of Electrical Inspectorate Government of Kerala. And it is my honor to facilitate today's safety webinar. I'm Nanda Kumar, convener of HSE Forum and Senior Associate Vice President of Carborundum Universal Limited. I'm happy to say that we received very good participation to all our webinars, and today also I hope to see more people joining in next few minutes. Last few webinars we had 40 plus, so we are at 32. We're close there. So hopefully we will have 45 plus to this webinar also. Our past 4 webinar talks that we conducted yesterday, day before yesterday, from 27th onwards, we have been conducting the safety seminar, specifically on electrical safety related to industries, related to buildings, electrical safety related to homes, and also on the importance of electrical safety in industries. Today's topic is a departure from our earlier talks. Today, we will be discussing specifically on the hazards caused by electrical arc and mitigation strategies. The talk will hopefully cover on various aspects, including what is an electrical arc, what causes electrical arc, how dangerous an electrical arc could be, and how do we safeguard ourselves against electrical arc hazards. To speak on this important subject of critical interest to any electrical engineer, we have with us an expert subject knowledge specialist with us. Mr. Jobi Jacob Joseph is an electrical engineer with more than 25 years of experience in the field of electrical engineering and sustainability. He's currently employed with ABB. ABB requires no introduction, a big company, and into the electrical business. And he's in one of their business units called Motion and working as Global Electrical Safety Manager. He's a qualified internal auditor and a lead incident investigator with significant experience in several industries, which include manufacturing, engineering industries, construction, public services, and utilities. So on behalf of HSE Forum, I extend a very warm welcome to Shri Jobi Jacob Joseph. He's joining us from UAE. Thank you, Mr. Jobi, for joining with us today. Looking forward to your talk. I also welcome all participants attending today's session. I'm sure we have a lot to learn from today's session. I request all participants to keep their audio on mute mode during the talk. Any questions that you may have, you can post it in the chat box. We will take it up after the talk is over for answering your doubts. And once again, wishing a very warm welcome to all of you. I now invite Mr. Jobi Jacob for delivering the technical talk. Over to you, Mr. Jobi.
Thank you, Nanda. Welcome all.
Most welcome.
First of all, thanks for National Safety Council as well as the Electrical Inspectorate to organize such an event. It's really happy to meet you all and to share what all things we know, right? So it's always in this discussion also I'll try to share my experience in this field. Being an electrical engineer, being a part of the electrical safety, and being a part of a renowned company, we have the experience and we have shared our own experience, what all things can happen when it comes to electrical risk as well as the arc flash hazards actually. So please feel free to ask anything. Those things which I know, I will certainly share with you, happy to share with you. If I don't know also, probably we can get some information from our network or from our colleagues also. So since the timing is very restricted actually, so I think quite a long topics to cover. So we can discuss after our talk actually. I don't have any, if you have time permits, so there is no problem in discussion also actually. Yeah, let's start to the course. Yeah. Introduction already be given by Nanda. Thank you, Nanda, on that. So start with the basic electrical hazards of electricity. It starts from shock, arc, and blast actually. I'm just, because of the convenience, I thought that we try to look through a lot of videos so that it's more easy to understand. And if anybody has got any language barrier, if somebody wants to speak in Malayalam also, please let me know. Then we can do in that manner also. So a typical electrical shock scenario in life. We can see that in electricity, we used to pluck mangoes and all those things, and people get electrocuted through that metallic pole, right? So this is a right example of the unaware things happening with the poor people, right? So yeah, let's start with that. I just want to warn you, there are some photographs or some videos which may not be pleasant. This is the real life photos or videos, so please be aware of that actually, yeah. I'm moving on this video because it's so disturbing. So what really kills you? So you see in the video also that in a fraction of a seconds, people die, right? So what is 50 volt is enough to kill you? That's the question actually. So um, basic Ohm's law, applying basic. So if you are working in a 400 or 440, applying the Ohm's law, taking the voltage and approximately a human skin resistance considering around 1500 ohms actually, you can see that the current in milliamps you get around 29 or 30 milliamps actually. So anything further to that is potentially dangerous to us. So roughly we say that 50 volt, anything above 50 volt AC or DC could be potentially dangerous and it can kill you actually. So at 30 milliamps, the respiratory paralysis starts. So this is an approximate. So 1 milliamps you get perceptibly a perception threshold. 3 milliamps you get a mild sensation. 10 milliamps you get a painful sensation. Again, it is depending upon the time also. 30 milliamps, the paralysis, you cannot release your grip, whether it is if you are contacting with an arm or grip actually, the paralysis threshold start, you cannot release the hand grip. 30 milliamps, the respiratory paralysis starts, your heart started affecting if it's passing through your heart to the ground. So stoppage of breathing happens. And 75 milliamps, the fibrillations, the heart started beating in a regular manner, and around 0.5% uncoordinated heart actions. 250 milliamps, it's almost 99.5 uncoordinated heart actions. And 4 milliamps, it's almost your heart stops. Maybe an artificial resuscitation can restart your heart, but after that, it's all about tissue burning actually. So
Electric
video
shock
on
affects
electrical
the
shock.
human body in three ways. It can interfere with the function of the heart, it can damage body tissue, and it can cause involuntary muscular contractions. The body's functions are regulated by minute electrical impulses in the nervous system. The reason the heart muscle beats is because an electrical signal initiates the contraction. An electric shock can interfere with this signal, causing fibrillation, which is a disruption to the heart rhythm. The damage electrical current causes to nerves and body tissue often goes unseen. However, severe electric shock leaves obvious signs in the form of burns. When an electric current passes through the body, it takes the path of least resistance and has both an entry and an exit point. The body's resistance causes heating, often resulting in excessive external burns as well as internal nerve and tissue damage. Electric shock causes muscles to go into contraction. Currents above 10 milliamps can lock the muscles in a contracted position, making it impossible to release an electrified object. Conversely, contractions to other muscle groups may violently propel the victim away, leading to trauma injuries. When the body becomes part of an electrical path, the severity of the shock depends on three elements: the path of the current, the amount of the current, and the time in contact with the current. The most dangerous path for electricity travelling through the body is for it to pass through the heart. As little as 50 milliamps of current can trigger cardiac arrest. The real danger of electric shock is not voltage, but amperage, or the amount of current. As the amount of current rises, so does the damage to the body. Symptoms include severe burns, respiratory paralysis, cardiac arrest, and internal organ damage. The severity of injury is also dependent on duration, the time that current passes through the body. For example, 1/10 of an amp passing through the body for just 2 seconds is enough to cause death. There's no such thing as a mild electric shock. All electric shocks have the potential to kill.
The video clearly states the potential hazards with the electrical shock and the factors which is involved in determining where you will survive a shock depends upon the voltage, the duration, the current path, and the resistance actually. Let's straight away go to the topic, the arc flash. So what's an electrical arc and what starts the arc, what puts out the arc and all those things. So you know that an electrical arc is like an ongoing plasma discharge resulting from a current flowing through a normal conductive media such as air. So what happens if you have two conductors and increase the voltage between these conductors? So air is supposed to be an insulation medium. So as the voltage raises, the air starts breaking down and it ionizes and it becomes a conductor of electricity. We must have seen the corona effect when you have the gang operated switch in a rainy season or something like that, right? So I have a short video of such kind of arcing. Let's see.
Your whole stick. Go upward with it.
You can clearly show the arcing there, right? So arc flash is a voltage breakdown of the resistance of air resulting in an arc, which can occur when there is sufficient voltage in the electrical system and the paths to ground to the lower voltage. So what stops the arc? Basically, when you stop the circuit itself, or when it trips or completely disconnect itself, or the clearance distance increases. So that's how we stop the arc. Otherwise, it will continue arcing. An arc flash within 1,000 amps or more can cause substantial damage like fire, injury, and massage energy released in the fault. Basically, instantaneously vaporize the metallic conductor. Normally, the copper expands 65,000 times generally, and it gets splashed like a molten metal splashes around the surroundings actually. And the metal and expanding plasma activates the extreme force. So the effects of arcing flash can be devastating if you are standing in front of that actually. So the intense thermal energy can cause severe burns within a fraction of a second, right? So the temperature of an arc can reach, it's termed that it can reach up to 35,000 degrees Fahrenheit or about 4 times the hot surface of a sun. So one of the major causes of electrical burns and deaths to our case is the ignition of non-fire rated clothing due to an arc fault actually. So when you are standing there, if you are wearing with normal clothes actually, so you get an arc flash. So you have an instantaneous reflex action is also there, right? So, but already in that fraction of a milliseconds, your cloth gets fire and the intensity of burn is related with that further that cloth burning actually. So for example, if you get an arc flash and you get a burn in your body of around 50% actually, and if it's more than 50%, the chances of survival is very little actually. So what happens during an arc? So an arc flash blast occurs around 12,000 degrees Celsius. It's emitting molten copper particles across. Normally it travels around 1,200 kilometers per hour. It includes shock wave. So if you are in front without any kind of ear protections, you could be temporarily or permanently deaf. The radiation, the heat wave, which ignites you, travels around 300,000 at the speed of light, basically. And it is also related with burn injury through arc radiation, noise and pressure injury. And if you are inhaling, suppose if you are racking in, racking out the breaker, if you are inhaling that hot fumes, your internal organs can also get damaged, right? So your whole body is under the risk of getting exposed to that huge electrical flash shower, basically. Arc flash is arguably the most deadly and least understood hazard faced on daily by the personnel working or within or near to the electricity. So what starts an arc? What causes? What are the conditions which can? Most of the people in arc applying to great potential difference across the gap, we can start an arc putting back something conductive in the gap, and we can draw an arc by starting with no gap, that producing a gap with current is flowing. So mostly when people are working in a near live equipment, think that probably it is de-energized or dead, and you try to play with that and resulting into a flash shower, um, and known to be live, but try to work in that. So again, it's related with the human error. Accidental contacts with cables during excavation, accidental contact with energized part during switching. So switching is very, very crucial. So when you do switching operations, rack-in operations and all those things. So operational maintenance, commissioning, testing and commissioning and all those things. So normally you do that, everything de-energized. You use a permit systems, everything is isolated. The human factors, when you keep something, forget your tools or pliers and all those things. And normally everything is nowadays controlled from the SCADA. So you told that the permit is being cleared, you can ask the SCADA to switch on, but your tools are still lying there or the earthing is still not removed properly. When you rack in, it straight away create an arc between the bus bar, since the bus bar is live, creating a huge flash shower. The other things include the physical failures resulting due to dust and all those things not properly maintaining. So the dust, if it get too much of dust involved, it reduces the current carrying capacity and the heat propagating capacity of the conductor itself. During testing and commissioning, it can happen due to wiring issues, aging, corrosion of the equipments and parts, and lack of proper work procedures. These are some of the things can create and starts an arc. So the main thing is that we are at the greatest risk of causing an arc when we are changing the state of circuit. It could be crack-in, it could be opening the panel which is full of dust, and these kind of things you need to be really careful actually. So particularly if you are working in an utility and all those things, when you are operating an RMU or if you're operating a switch gear, when you are opening a door and all those things, these are part of the training, safety training requirements where you stand at that time, right? Arc flash or arc blast, when an arc flash or fault occurs, a massive electrical explosion can erupt, and the heat and light emitted by this explosion is called arc flash, and the pressure wave is known as arc blast. So an arc flash normally releases hot gases and concentrated radiant energy up to the 4 times of the sun surface, which can melt, which we already discussed about it. Let's take a video. This is one is related with a medium voltage switch here when you are particularly working in substation environment, and the other one is related with a low voltage environment. So sometimes people often think that, yeah, the medium voltage or the high voltage is more dangerous, the low voltage is not so dangerous, right? So watch it. So what is really happening here actually? Yeah. These are real-time incidents got recorded through the CCTV. And let's watch on to the low voltage environment. I still don't remember why 3 people are working in that environment when people are doing troubleshooting um, uh, or anything doing with that panel, in particularly in low voltage. See the explosion level. It could be equally devastating like a medium voltage, right? So um, let's see it in a slow motion, how the arc engulf somebody is in front of it, and it happens in a few milliseconds. So we take it on a slow motion basis, actually. You can see the copper particles expands and melts and splash over. So if there is a wall, your superimposed image will be splashed on that wall itself, right? So, and the entire body is being engulfed in an arc flash, actually. So it doesn't matter which part of the body, right? So you are completely engulfed in an arc flash, and it happens in a milliseconds, actually. And it is associated with these fumes. So if you inhale these fumes, for example, if it's a SF6 breaker, so it gets decomposed into sulfur and fluoride. So ideally, sulfur and fluoride is highly toxic. So you, even if you get survived from the arc flash, probably you are inhaling these toxic fumes can literally kill you, actually. Effects of arc flash and burns. I'm just reminding to the team, there are a few disturbing pictures are there. So if you don't want to watch that, please make sure that you don't see that. So what are the different types of burn injuries? Normally, what do you mean by a first degree burn? Normally you get from sunburn or no blisters. So the skin itself can regenerate. Nothing happens to that. Probably the outer skin maybe peel off. So what's a second degree burn? For an example, a candle burn or candle wax fell on you. So your outer skin blows up. You have blisters. Again, but it's also a second degree burn. After a few days, your skin can regenerate. But normally, in a real arc flash, you get second and third degree burns. In the third degree burns, your deep skin scare is completely charred. No skin regeneration is possible. So you may need to graft your skin from other part of the body. And if it is too much, it is not possible also. So as I told you, some pictures are really disturbing. So these are the real-time pictures. So I just want to type some of the electrical injuries you can have. So when you get contacted with an electricity, you can see the entry point and the exit point here itself, actually. So that's a contact with any kind of live electrical um, wire or cable or anything like that. How a flash looks. So this is like if you are standing in front of an arc flash, it scatters to your body. You get mostly a second degree burn. Your outer skins are completely burned off, actually, and the percentage of burn is very crucial here, actually. So if you are wearing a non arc rated garment in such kind of scenario, so there is a high probability that the burn continues even after the arc flash. There normally the arc flash comes and goes, but you get maximum burns because of the your cloth gets flash over and it keeps on burning. And particularly cotton is even though cotton is initially it's a little bit retardant up to 4 cals, if it's more than 250 GSM. But once it starts burning, it keeps on burning and it's very difficult to quench, actually. But if you are using a terracotta or nylon thread material, actually, it literally melt and stick to your skin. Then it's very difficult to remove that part also. So that's one of the reasons when we say we have technological advancement to quench the arc flash, but at the same time, the human factors we cannot avoid, right? So we are in front of in such scenario. So that's why we try to make sure that you are adequately protected from the PP perspective also. Now that's a flash injury. This is an arc injury. So this is what exactly happens. So you are cooked basically. So you can see the internal flesh is itself. It's a third degree burn. So if you get such kind of burn, the only possibility is The only possibility is probably you need to amputate your body or skin, actually. Yeah. Then how will you determine where you stand in such kind of things? Little bit about the arc flash boundaries. Somebody is talking. Yeah. Can I mute them? Cannot mute Marily. Yeah, thank you. Yeah, arc flash boundaries. So the distance a person must be from an arc source to receive just a curable burn. So if you are standing in front of a panel for any kind of switching or anything like that, so generally this level of burn is described as a second degree burn. So if you get an arc flash, so if it's a curable burn, that's the area where you can stand, particularly when you are doing any job or any work or anything like that. Possibly that's the area where you can start working on that area, right? So and the energy received from an arc flash or from bodies, and therefore the arc flash depends upon exactly the following parameters: the voltage, the length of the arc, the magnitude of the current involved, the voltage short circuit current in that arc, the duration of the arc, and the distance where you are standing from the arc, actually. So we are usually not be able to get the information required to calculate the arc flash boundary. If you have done a short circuit study, yes, probably you can get all these parameters, and we can use an arc flash calculator, actually. So little bit on the arc flash boundary. So you see on the right hand side, if you are too close, where we are in front of the panel, we call it as export energized conduct. This is a restricted approach boundary. In this place, you are not only vulnerable to arc flash, but you are also vulnerable to electrical shock. So a technician or an electrician in that workspace should be adequately protected. When I'm talking about protected, he is in front of a live panel, which has got a potential to have some sort of failures. Then he is vulnerable to all kind of electrical shock as well as arc flash. So that's the restricted approach space, basically. So further to that, if you're too close, we call it as prohibited approach space. Restricted approach space is further to that. For example, if you're standing in front of a panel at the door, so that's the restricted space. If you are inserting your hand towards to the panel door, inside the panel door, and that's a prohibited approach space. Further to that, you have the limited approach boundaries. That's the area where you can still have an arc flash injury, because the arc flash can travel depending upon the following parameters we have discussed. Still you are vulnerable to that arc flash. You can get a burn injury more than second degree burn. And when you calculate the area where you stand is the arc flash boundary, that's the area where it's safe to have to get the maximum incident energy can be less than a second degree burn, actually. So even you get a splinters or anything, you are safe, and you are in a safe distance, basically. Yeah. There are various methods of calculations to arc flash boundary. I mean, I'm not going through the calculation at this class, but probably I can share. So what ABB is doing, we have different kind of environments. Some people are working in service environment. Some people are working in factory, where manufacturing facility environment and all those things. So when we initially started this arc flash study, we have created a matrix, basically, depending upon various parameters. And we try to include different kinds of parameters like voltage, current, the short circuit current, and where you are safe. So for example, if you are working in a completely green field in a de-energized environment, but inside a substation or in a dangerous in a factory environment, actually, we still prefer that our employees or the employees should wear an arc flash PP as a base minimum wear, so that you are working in an energized or in a substation environment. So there could be some sort of dangers. The basic minimum PP should be a category 2. I will come to that actually. So they get a basic, that is like a uniform. So it is not like olden times you need to wear so much cumbersome boiler suits or something like that. So instead of wearing a normal coverall, instead of that, you try to protect them with a arc flash coveralls actually. And nowadays the cloth materials are also improved, so you get the basic minimum protection. So anything below 50 volt, 30 volts plus or minus 10%, anything below 16 amps, even the short circuit current is less than 1 kilo amps. So ideally, you don't need to wear anything because there is no potential arc flash can happen, but still we prefer that the minimum PP. But at the same time, if it's above 50 volt, 480 volt up to 480, where short circuit current is again around 1 kilo amps. And if it is above 16 amps, you get your not only your body, your hands, as well as your feet. You should have an electrical rated shoes. It's not only arc flash risk, shock risk is also there. And if you are above 480, around 480 volts, more than 16 to 63 amps, you are full body protection. So that's the area where the current carrying capacity is higher and the incident energy could be higher, then your full body protection should be protected. So the column C protects from your full body. You protect your body plus your face plus your hand and plus your feet actually. And depending upon the voltage goes increases up to 40 kV, you go up to the 40 kA, you go up to the category F, and you get protected to the maximum. That's the 40 cal centimeter square. If anything, the incident energy is more than 40 cals actually. It is very impractical to get you protected by wearing a PP. So rather than we adapt engineering controls like remote switching and all those things actually. So and at the same time, let me see it is working or not. We have created a calculator also. If it works, it's well and fine. So let's see this calculator works or not actually. Let's see. I hope you can see my screen, right? Yeah. The calculator part. Can anybody confirm?
Yes.
Yeah.
Yeah.
It's taking a little bit time. We have defined this calculator based upon our application. So nowadays, the metrics is a little bit outdated for the engineers who are you can use the standards. Normally, we use NFPA 70 or IEEE standards. IEEE standards could be the 1584 2016 to 18. You can use that standards actually, or these are the standards we normally use for this calculator actually. So we can, so ideally when you do the calculation, there are 4 parameters we are considering. One is the system voltage that we can get it from the nameplate, your upstream overcurrent breaker device current. What is the upstream, the current rating of the breaker, whether it is 100 amps or 200 amps, basically your bus bar rating. And third parameter, which is the short circuit current carrying cap. What happens if a short circuit happens? So if you are done a short circuit, for example, let's say a 2000 amps or 1500 amps bus bar can get up to 15 to 20 times the maximum value to the short circuit. And it add-ons if you have inductive loads connected to that, right? So it will get add-ons. So that will be considered as the capacitive load also. So it's very difficult. Sometimes it's very difficult to get that. But at the same time, these parameters you can get, and we keep the distance as a constant. Normally it is kept as 18 inch or around 48 centimeters, right? Like that's a constant value. And the other important thing is your relay settings, how you set, whether it is instantaneously set or a time delay or something like that. So this is the common mistake also people does. In order to increase the reliability of the machines or the equipments, actually, people take the opening time much higher actually, so that it should not trip. And that's one of the biggest challenge for people who are working nearby. For example, if you keep the opening time in this 480 volt itself at 0.5, and let's say the short circuit current around 40 amps or something like that. So you get probably an incident energy around 29 calories per centimeter square. For example, if you keep this opening time around, let's say, 0.3, straight away the incident energy reduces to 17.6 calories per centimeter. And if you keep the point time to, let's say, 0.2, it's 11. And if it's less than 10 milliseconds, the incident energy is considerably reduced. So if you do an arc flash study in your own premises, actually, this is how one of the way you can reduce or mitigate your arc flash energies, right? Coming back to the slides, sorry. So based upon that, when you do an arc flash study, based upon that, you paste an arc flash labeling, a warning. So in that label, you get the maximum arc flash boundary. So where you should stand, how much clearance distance you can have it. So if you have different panels or different breakers or different feeders in a switchgear room, possibly what is the highest in that? That is the arc flash boundary for that particular room, actually. And normally we try to paste in every feeder panel, whether it is low voltage or medium voltage. The required arc flash study is being calculated and the arc flash label is being pasted, and it will give you the incident energy in a condition where the panel doors are open. So normally, as per the IEC requirement, if all your panels doors are closed, the arc flash should contain inside. But in reality, it doesn't happen actually because of due to the poor maintenance, or if anything, the criteria that they are telling is not met, then it will propagate out actually. So then it will recommend the required PP, and the limited approach boundary, the restricted approach boundary, and all those things will be mentioned in the arc flash label actually. So and nowadays it's not so complicated. People can do arc flash, not study, but at least arc flash risk assessment can be done internally. No need to, so if you are only thinking about what level of incident energy is coming out from that and what level of PPE we need to wear, we can do it through an arc flash risk assessment. If you want to do how to mitigate the arc flash incident energy, then you need to do a detailed arc flash study, and we have to find out an arc flash mitigation solution. And there are several ways we can mitigate the arc flash due to various engineering controls can be put in place, not only the calculative way actually. Yeah. Again, a little bit on the reasons for PP. The full current, as the full current increases, the arc flash boundary also increases actually. So this is a rough calculations based upon the NFPA 70E, the American standard. So 1.2 meters, 4 feet for anything up to 1000 volt systems, and 1.8 meters up to 6 feet up to 36 volt system. It may not be 100% accurate. This is based upon the experience of the calculations they have done actually. Testing, a little bit on the testing side. There are various types of testing. So the recent testing is IEC 62447, where you use, I'm not in my slide, it's slightly old way of open box test, what we are doing. The new test method is also considered about the panel size, the vertical panels or horizontal panel, and the depth, and all those things are also. So that's the standard IEC 24. So the panel test basically. So otherwise the clothing test is done by IEC 61482, what level of PP and all those things. So it's like a mitigation level further to the engineering controls actually, and what level of PP. So basically it is calculated on arc thermal performance value, ATPV, and calculated in the incident energy. So you get in kilojoules, then it's converted to incident calories per centimeter square actually. Just for your information, to stimulate, this is called an in a box test, that when you are near to that actually, the standard is 61482 1 and 2. Yeah. and I don't want to go into detail onto that. Actually, these are some of the tests you do, and these are the guidance as per the American standard NFPA 70 on the protection level coding. So there are several categories: Category 1, Category 2, Category 3, and Category 4. So this is the categories we are considering normally when you can wear a wearable type of PPE, right? If it is more than that, so for example, if the incident energy is more than 100 cals and all those things, and particularly nowadays, everybody is fond of batteries, and battery can produce huge DC arcs, right? So the incident energy could be very, very high actually. So this is one of the biggest headaches nowadays from manufacturers like us we are facing. So how will you prevent people from such kind of huge DC energy where the incident energy, when all these string systems are connected in series, the incident energy can go up to much higher capacity where the PP will not be able to do. So we talk of automation and all those things in that picture. So this video shows about the PP testing related with the non-arc rated. So the normal workwear actually, how the arc is getting propagated when a flashover occurs, right? So you can see that arc comes and goes, but still the cloth is on fire actually. So that's a potential danger you are facing. So that means the arc comes and goes, that part of the body will be affected actually. But if the cloth is a non arc rated, like natural or cotton or other terracotta fibers, actually it keeps on burning, and your percentage of burn is increased. And if the percentage of burn is increased more than 50%, your survival chances are very little actually. So I was searching for a lower category PP, but I got it this one actually. So this is related with a 40 cal suit in front of a medium voltage switch breaker. What exactly happens when an arc flash burns, right? So
this mannequin is wearing Westex Ultra Soft 40 carry flash suit, and he's up on a ladder because folks asked us what happens if an electrician's up a ladder. So we're faulting the upper bucket of the motor control center. It's a 45.7 calorie arc. Very large arc. There's a ton of molten metal coming out in all directions, but there is no fire on the garment. You'll see when our firefighters come in and turn the mannequin around that there's also no break open, showing that even in a 45 calorie arc, the Ultra Soft provides sufficient protection. We get a look at our split screen slow motion, and at 3,000 frames a second, this is a 14 cycle arc. You get a great look at the pulsing of these cycles, and you see that the molten metal comes out as a wall. There's a wall of molten metal going in all directions, and the arc eventually defeats the sides of the MCC as well, and we get the arc plasma out to the right and left of the mannequin. This mannequin.
Then this is related with the PP part actually. But when it comes to the switchgear part, what kind of test, arc resistant test as per the 62477 IEC actually. So this is a real test environment where our panels are getting tested. So when an arc occurs due to some internal failures or short circuit or a physical failures actually, normally the heat travels up, right? So every panel should have a heat vent. So when you are doing a switching operation and all those things, where are the areas where you need to stand behind? When you, particularly if you are operating in RMU or anything like that, don't stand on side or anything. So probably the explosion vents are at that side, and it can certainly, or if you are standing in front of a breaker or a panel actually, where you stand on the hinge side or on the door side actually. So if at all an arc flash happen, if you are at the door side, then the door can open and the flash can happen and hit you if it doesn't have a proper kind of explosion vent. If I don't know whether you are using an ABB medium voltage breakers, unique gear breakers, you can see the trapezoidal shape at the top. So whenever an arc flash occurs, the heat propagates out and it is expands and it goes, and the exit is through that trapezoidal tunnel and it will go somewhere else actually. And there are also other kind of protections normally we use related with arc flare detecting sensors, so that whenever an internal flash or a arc occurs, actually it senses it and it immediately trips the circuit actually. So there are various methodology we have adapted when it comes to the arc flash mitigation part. So I would like you to go through the switchgear test. Actually, normally what they do is that they create a three-phase bolted short circuit test inside a switchgear, and they keep cotton outside and wired cotton outside. Actually, if a flashover comes out and burns the cotton, so then the test fails. But if it is not, but at the same time they have an explosion vent is also there, so it only passes through the explosion. Let's watch that. The test failed. So these are some of the tests in real life we do with our own panel, any panel. I mean, if it is as per the IEC 62477 standard, then it has to contain those arc flash inside that panel itself. It should not come. So that's an arc designed panels or breakers actually. For the arc flash mitigation, we noticed that there is a clear hazard is being identified. It notes that it has happened and still it's happening. The consequences can be fatal, can be disfiguring, involves lost time. So what's the standard say? Always the law says that as far as reasonably practicable, it shall be done, or a practical solution is there. Again, it's reasonably balancing of the cost, financial effort, and time. So the risk may be death from electrocution and the cost of insulation material low, then the level of duty to prevent the danger approaches is absolute. And deception of production is not deemed as an unacceptable cost actually. There are various standards, particularly IS standards in India, 5216 recommendation on safety procedures and practices in working electrical work. I also know that we have an electrical handbook or something else recently created by the national safety. Then normally we use when it comes to the arc flash standards, American standards are predominant. The NFPA 70 OSHA requirements, that's Occupational Safety and Health Administration requires that every switchgears panels has to be arc flash studied particularly, and it is coming up. It's moving from America to Europe, and for some of the companies in India also, particularly started with utilities, oil and gas, and all those things. It's coming up actually. Outcomes, this is more related with our own incidents actually. So mostly we find that burn injuries are the predominant one. 70% comes from burn injuries, and hand fingers are mostly exposed to that. And we try to include the standards when inside ABB. All these standards have been trying to get for the clothing part actually, and we try to adapt the NFPA standards also. Again, hierarchy of controls is being adapted. So if how we can eliminate such kind of arc flash risks, what is the substitution, how you replace the hazard, some engineering controls which we already discussed about it, and administrate. And the last resort is on the PP. So what we noticed is that even though we have all kind of these controls, but still injuries are happening. People are vulnerable to such kind of risk. People go near to the panel. We do troubleshoots, we do testing and commissioning. So they are vulnerable to such kind of risk actually. For a hierarchy based upon the evidence like avoidance, ensure that the work is being clearly planned, organized, and free from any kind. So proper isolation is being given when you are working in and around such kind of devices. Make sure that only skilled authorized persons are worked. Non-technical people are not supposed to use voltage rated tools, particularly in low voltage environment. Isolation, if you can isolate, remote switching and all those things, that's more. Risk controls includes, we call it as 7 steps that save lives, which I will show you. Proper isolation, locking out, tagging out, earthing and all those things, so that when you are working for a service or a maintenance job, you 100% make sure that everything is isolated actually. Reducing hazard by design. So 3 key factors, arc flash, the factors, the fault current available, the time, and when the arc flash is being cleared, and the distance where you are from an arc actually. So various design of equipment choices can be made. Fault current. So the simplest method is that adjust the fault current in your relay settings and all those things, so that the operative is always being protected accordingly. Arcing time. The arcing time can be reduced by setting up the protection devices. Then the distance remote operations can be used. Nowadays, it's also used rack in, rack out breakers mechanisms are there, so that the operative doesn't needs to be too close to the panel actually. Yeah. We have a methodology called ABB 7 steps that saves lives. There are 7 steps we do when you do a service or a maintenance job, particularly when you go to a customer site and do the job. Now, before I play that, I would like to ask Nanda, do we have time to play that? It takes around 8 minutes actually. Do we have that time, or we need to?
Yeah, I think we can go. It's quite interesting. Let us go through it.
Okay, so this is purely to a company specific actually. So this is how we work when you are working in a service environment and all those things actually. Let's play the video. There are various types of videos are there. I choose the high voltage, preferably. I was thinking of the electricity board environment and all those things. So we have medium voltage and low voltage also actually similarly. So let's watch. Yeah.
Working with electricity is common in most business units in ABB, and no one understands better than you the extent of the risks you face on a daily basis. You have received training on electrical safe working practices, the processes for risk assessment, and the application of the hierarchy of controls to either eliminate or mitigate electrical risk to an acceptable level. You have a full understanding of what you have to do to keep yourself and others safe, and all of the necessary elements to create a safe working environment. At times, you may, due to time pressure or customer pressure, consider not following these practices. Don't do it. In this scenario, the ABB engineer arrives at a client site to perform some switching and maintenance work. The customer requests that the work is carried out without full isolation to reduce disruption. Remember, you are expected to be the expert, and customers often underestimate the risks of working on or near electrical lines, equipment and systems. As a result, you may be asked not to place the equipment in a safe working condition because they're concerned about lost productivity. You must politely and respectfully refuse. You need to respectfully help the customer understand why it's in their best interest to follow good safety practices. Explain that based on your experience, you believe the best thing to do is de-energize, verify, secure, and in most cases, earth or ground the equipment before proceeding with the work. Your main goal at this time is to help the customer understand that following your advice is in their best interest, but there will be times that you will not be able to convince them. When this happens, apologize to the customer and explain that you do not feel safe or comfortable doing the job. This is a good time for involving your manager in the decision not to proceed with the work. The bottom line is, you should never do work that you feel is dangerous to you and others in the area. When you are comfortable that you can safely perform the work, there are things you must do to ensure the highest possible level of safety. These are the 7 steps that save lives. Step 1. Prepare for the work. Do an on-site risk assessment or a job hazard analysis and be in possession of a clear work order to execute the work. Where required, the access or work permit is to be obtained by a person who is authorized for the specific electrical system. Engage the person responsible for electrical equipment or system to review single-line diagrams, schematics, and switching plans. Ensure the competence of workers. Check for proper tools for the job. Determine and select the proper ARC-rated personal protective equipment, PPE, and associated PPE as defined in the ARC Flash risk assessment. If an ARC Flash risk assessment has not been conducted, then the ABB matrix shall be consulted to determine the appropriate ARC-rated and electrical PPE. Finally, decide on the appropriate work methods and initiate the permit to work process. Step 2. Clearly identify the work location and equipment. Use your senses to identify problem areas. Define the work area via barriers and barricading, and label the equipment by placing warning notices on any adjacent panels you're not working on. Also, avoid distractions such as talking or texting on the phone. Step 3A. Disconnect all sources of supply. Where possible, ABB recommend that switching should be conducted remotely. If not, observe switching from a safe distance well beyond the ARC Flash boundary. If switching is performed prior to arrival, walk down the equipment to check the isolation points upon arrival. When required, perform switching only if properly trained and while wearing the proper PPE identified in Step 1. Step 3B. Secure against reconnection. Secure against reconnection by applying lockout-tagout, and if possible, avoid allowing other work to take place at the points of isolation. If there are multiple points of isolation, group lockout-tagout shall be implemented with the person in charge of work, or PICW, acting as the group lockout-tagout leader. Step 4. Verify the absence of operating voltage. Utilize only properly rated and calibrated voltage detection devices and wear the proper PPE identified in Step 1. It is extremely important that you test the voltage detection device on a known live source or by using the detector's test button if designed into the device, then test for the absence of voltage. Ensure to test for loss of voltage on all 3 phases where 3-phase applies. Finally, test the voltage detection device once again to ensure it is still working properly. This 3-step method is required without exception. Step 5. Carry out earthing and short-circuiting. Close and lock earthing switch if applicable, or apply portable equipment for earthing and short-circuiting while wearing the proper PPE identified in Step 1. Also, use insulated tools when required. Be sure the equipment is free of any residual charge or induced voltages and short-circuit any fault current. you may need multiple earths between supply sources and the point of work, commonly referred to as local earths. Ensure that you earth both sides of the apparatus being worked on. Step 6. Protect against adjacent live parts and take special precautions when close to bare conductors. Determine minimum approach distances and apply screening. Take special precautions such as wearing the properly rated insulated gloves and leather overs and using insulated tools for inadvertent contact potential. This is especially important when marking live components or cables or while placing protective barriers or screens around the area as you prepare to do the job. In especially dangerous situations, like working closer than 1 meter to the live connections, or where there's low lighting, difficult access, or higher voltages, take extra precautions. Now that you've created a safe work area, you need to take the final step before beginning work, which is Step 7, complete the permit to work and walk the permit. The PICW now gathers the working group and together they walk down the permit to work to check isolation points, verify all circuits are isolated and secured, ensure all parties are integrated with the lockout-tagout and check that the earths are properly applied. The PICW then answers any questions from the working group, ensures the work can proceed without danger and validates the permit to work. The person responsible for the electrical equipment or system at the job site or permit issuer then signs the permit to confirm that the facts have been communicated. You will also sign on to the permit confirming that you understand the safety aspects of the job and agree that it is safe to begin work. The permit to work formally documents many critical facts about the job, including the scope of the work, where it will be done, the safety precautions taken, and individual responsibilities. Understanding and agreeing to these facts is essential to the safe completion of the work. Once you sign, you are responsible for ensuring the safety of yourself and anyone else in the area while doing the job. You can't change what's been described in the permit without the agreement and signature of the permit issuer. Remember to be aware of induced voltages from nearby equipment. And of course, you should wear all of the appropriate PPE for the job. Make sure anyone working in the area, especially people who don't understand the dangers of electricity like crane drivers and civil contractors, know where the live parts are located. Continue to reassess the risks, asking yourself these questions. Are there any issues with the live equipment? If this equipment fails, could it affect your safety or the safety of others? Could you directly affect live parts, particularly when handling cables or conductors or using large plant equipment? Could you indirectly affect live parts, for example, interfere with earth conductors, protection and control supplies, or heating and cooling? The PICW must conduct the pre-job briefing for the work team to be sure everyone understands how the job will be done and what safety processes are in place. If you leave the work area for a break or any other reason, you must sign off the permit. When you come back, you must engage the PICW to be briefed on any changes that may have occurred during your absence and sign back onto the PTW. As an experienced engineer, you are responsible for assessing each job and confirming that it can be done safely. If you aren't comfortable with doing the job, you should discuss this with the customer's responsible person and your manager. If you aren't able to resolve your safety concerns, respectfully decline to do the job and ensure the customer understands why. When you are confident that you can safely do the job, follow the 7 steps that can indeed save lives to ensure that the job will be completed in a safe manner and that you will go home healthy and injury-free at the end of each workday. Here are the 7 steps once again. Step 1. Prepare for the work. Do an on-site risk assessment of job hazard analysis. Step 2. Clearly identify the work location and equipment. Step 3A. Disconnect all sources of supply. Step 3B. Secure against reconnection by applying lockout-tagout. Step 4. Verify the absence of operating voltage. Step 5. Carry out earthing and short-circuiting. Step 6. Protect against adjacent live parts and take special precautions when close to bare conductors. Step 7. Complete the permit to work and walk the permit. Working with
Okay. Again, coming back to the topic, we are at the greatest risk when crossing an arc when we change the state of the circuit. The switching operations by nature can expose the person who want to take the operation to high hazard. So key requirements for consideration include switching can be carried out remotely, ensuring that the operator have the highest competence. There is a systematic and highly disciplined procedure, like 7 steps is being followed. Switching can be carried out dead and live operation confirmed by remote operating equipments, reduce the potential fault level, ensure thorough coordination assessment is carried out prior to the operations, check the maintenance ratings and commissioning history, certain operations such as insertion of switching device, potential fault closure, and exposure to such kind of crash risk. So standard development, apart from all these engineering controls or design controls, still our crash PP is a must as regarded as a compromise of mitigation of the potential failure, and there should be considered as a part of the range of controls depending on the risk level associated with the situations or the switching operations. We discussed about various type of hazard category, Cat 1, Cat 2, Cat 3, and Cat 4. So Cat 1 is up to 4 cals, Cat 2 up to 8 cals, Cat 3 25 cals, and you can attain it by layering also, not directly going for a Cat 3. So during the switching operations, you can have the 8 cals plus an 8 cals with the air gap, you may get up to 25 cals actually. So that's the studies being calculated on that. So you don't need to wear the cumbersome 25 cals or 40 cals directly actually. So if it is above 40 cals, so you can have a 25 cals plus an 8 cals with the air gap, you may get up to 40 cals actually. That's how we manage. It is not about PP, it's about head protection, face protection, suitable rated electrical gloves, footwear, EH rated footwear. So normally the EH rated footwear are tested up to 18 kV so that the outer sole is tested up to 18 kV so that you get the installation resistance in giga ohms, not in mega ohms actually. Hearing protection and voltage rated tools actually. So this is the primary kit for inexperienced people working live near equipment actually. So this is like a additional things along with that for a competency level, a middle level competency level, and those people who are doing switching operation, this is what we are recommending actually. Apart from that, the basic tools could be insulated using screens and all those things. Earthing kits should be available. And not only when you give the PP, it's also about the how you take care of the PP, also washing instructions and all those things. The care should be also be a part of the training actually. Gloves, always gloves is like a life-saving equipment. So when you use the glove also, you use a leather protector. So leather is a natural arc retardant. So it's a mechanical protection also. So before you start using, you test the gloves. Even you can measure the gloves according to your palm size actually. Get the right gloves as per the class from class 00 up to class 4 actually. So you can get from 500 volts or 750 volt DC up to 36,000 volts up to 54,000 volts DC actually. Why we insulated gloves, where we insulate, particularly when we are into the prohibited approach boundary, when you are entering into the live working, so inserting your hand into your switchgear, it's always a habit to not to insert bare hands into any cabinets, even though it's isolated. There could be some source of supply from somewhere, or a leakage, or a backfeed, or from UPS, or from, if it's a permanent magnet moving coil motor, if it's turned on the other side, it can act as a generator. So all those things should be considered as a part of your risk assessment when you are entering or inserting your hand into the panel actually. So voltage detectors, so We are not supposed to use multimeters because multimeters are a measuring device, and there are a lot of cases where you use the multimeter and you are taking the measurement and somebody behind holds the multimeter and he suddenly changes to continuity. Then if it's a measuring, then you are in big trouble, right? So we multimeters is considered as a measuring device. We use voltage detectors so that such things should not happen actually. So there is, so I don't know, is that standard up to that? When it comes to the tools, when the high voltage detectors, make sure that it is checked, the 3-point contact check, check at the as known source, check at the area where you are working and recheck again. Use of earthing, insulation, discharging roads and all those things. So these kind of things you need to be considering actually. That's all from today from my side. I hope it was useful for all of you guys, and please feel free if you have any questions. I'm ready to have a chat actually. Yeah, that's it. Thank you very much. Yeah,
Thank you very much, Mr. Jobi Jacob. Very excellent presentation, and very keep us to the glue to your talk. And I'm happy that we had a excellent participation. As I said, like in previous today also we had close to 53 people joining us, and now we have still 40 continuing to hear you. The floor is now open. People, participants, if you have any doubts, clarification, use this opportunity. You can either post in the chat box or you can unmute and post it directly. Kindly introduce yourself also if you are asking directly also, so that the speaker gets to know where the level of answering would depend upon what level you are. So you can unmute and post your questions. So while the participants debate themselves to what to ask, I have one question. See, I have seen a lot of substations, including the electricity boards substation, including generating stations.
Yeah.
I've never seen anybody, and I'm just trying to be very upfront, brutally upfront. I've never seen anybody wearing the kind of PPEs that you are talking about during especially when during the switching on phase. You said that the biggest risk is during switching operations. The PPEs that are worn as normally the gloves, maybe if they are working on 11 kV, it would be 11 kV tested gloves, or if it is CHT 110 kV, or they would be wearing gloves to that extent. But I have not seen people, especially electricity boards, wearing those kind of PPE dresses to protect themselves. Of course, the other part is well taken care in terms of the 7 steps, life-saving steps, preparing for the work permit. All those things are taken, except for the PP side, little doubt. I'm just asking you this question: up to what level of voltages also this needs to be practiced?
Yeah, good question. Actually, it's like how we advance because if you see the anatomy of incidents, actually, it's alarming that the figures where people are getting electrocuted or flash or incidents are happening. So if you scroll down through that, actually, so it's really alarming. So we have all kind of these procedures are in picture, but still incidents are happening. So there is a gap. Certainly there is a gap. So we use PP as a what do you say, after the risk assessment, it's like a counter mitigation. What is the residual risk which can happen? And this is the area where your life is getting protected. As I told you, if you get a flash shower, if your burn injuries are more than 50% actually, and there is a survival chance if you go to the burn unit actually, and what kind of things they are doing actually, and your survival chances are very little. But if a PP is there, the technology is already there to prepare, and your burn injuries can reduce by 50%. Your survival chance are 100%, right? So that's it actually. And particularly, it's not only arc flash risk. Basically, when it comes to low voltage, a lot of incidents are happening based upon the shock risk, electrical shock risks, and people insert their hands without thinking into any. So, for example, in a motor or a drive or in a cubicle or something like that. So you may not have the main source of supply. You may have control supply, which anything above 50 volt, or you can have backfeed, UPS supply, and all those things are there. So that's one of the reasons that we, even though the engineering controls or systems are there, the PPs also become a part of it actually. And nowadays, people have a myth that it is too complicated and all those things, but it's not. Most of the PP companies are from India only, and it's instead of wearing a cotton coveralls, why don't you wear an arc flash PP actually? So it is fire retardant plus arc retardant actually. That's how we proceed, right? That's how we grow. That's the standard. We raise the bar a little bit, right? Yeah, that's how we work. Nanda, I hope I answered your answer, right?
Yeah, very much. Yeah. And there is one more query from the participant, Mr. Dhananjay Patil. Thank you for joining. First of all, it's an excellent presentation. And he goes on to ask, you talked about the multimeters should not be used. Can you explain something more about voltage detector? How to use it? And does that detect 100% surely, or any error is possible?
We need to use, I always recommend when you use multimeters, the problem with multimeters, I told you, I mean, it's a measuring device and it has got a battery source itself and it has got various type of parameters are there, right? Voltage, current, and all those things. So, and when you, in a real situation, imagine a situation, and in India itself, one of our contractors, when they're working in a solar system, actually, I investigated that investigation a few years before, where the employee was trying to, what do you say? They're trying to troubleshoot. So you have the solar plant, and the other side you have grid parallel through the transformer, actually. So the solar plant is isolated, but at the same time there is a power coming from power back from the transformer side to the low voltage side, actually. So he was measuring it. And to assist in a huge solar plant, somebody from the customer who is not a qualified person. So while he was testing, the guy at the back side was changed the multimeter into continuity, actually, and then it literally exploded onto his face, actually. So this kind of accident should be complete. That's why where the voltage, and as per the standard, the International Electrotechnical Committee recommends voltage detector, not multimeter. Make sure that the voltage detector is of right company. There is an approval process in ABB, not just a fake meter which is available in the market. Make sure that it is from a reputed company, right? That's it. Yeah, it's tested, so its certificate are available actually. I hope,
yeah. Mr. Dhananjay Patil, your question is addressed. Any BIS, for one more question from him, any BIS standard for
I have to check actually. Yeah, of course. I can share some of the, I don't know if the Bureau of standards of BIS from the India side. Normally we have the CE marking and all those things, international standards. Let me share whether I can find something from our SharePoint. I hope you can see my screen, right? So, okay. Global electrical safety. So, so we normally in the company, we try to approve the voltage detectors and all those things. So we have a list of voltage detectors which is being approved as per all the international standards have been met actually. So these are some of the global companies which is approved from our side actually. So there are we try to analyze through, we try to trial it. Ideal one which is available in India, probably Fluke, is very much common. There are some German companies like Elma. Femica is commonly used. The Fluke one, I don't see any Indian company here actually. I don't know. Probably it has not come to us actually. Megger is there. Testpo is very common one actually. So it meets all the international criteria. These and even some of our proving units are there. So you don't need to go to a known source like it's maybe a panel itself. So you are vulnerable to such kind of risk. So instead of that, you can have the proving unit so that for a self-detection from the low voltage scale. For the medium voltage, there are the same companies are there. I'm talking about the low voltage, which is so make sure that you have an approved company. Regarding the Indian regulations, it should have been covered actually normally. Yeah.
Right. I think his question is answered. There's a thanks message also from him. There's one more question from Mr. Sundarraj. Can you unmute and please post your question?
Hi, good evening, Jobi Jacob.
Yeah.
So the session was wonderful. The session, it was information centric. So my question is, Jobi, it's about the injury, right? That this arc flash causes. Is it a ordinary fire injury or something electro fire or any other very deep injury or electrical injury?
It depends. I mean, arc flash and electrical shock both are different, right? So the problem when you get an electrical shock, we all know that it takes the least resistance through the body, right? But at the same time, it takes all the paths through the body. It attacks bones, nervous systems, everything. So I can tell you a story. I worked in Dubai Electricity and Water Authority. So I have a friend working in customer side. So he get an electrical shock from a customer DB. And he was okay, nothing happened to him. But after a few days, we noticed that his hand, particularly where the path where the electrical shock has been taken care, his veins started dying. And finally, he has to amputate his hand to prevent his life, actually. So basically, the flow of current can damage all kind of body tissues, actually. So in a fire incident, initially it is acting to the skin, the outer skin actually. But in an arc, the electrical energy can pass through that along with not only flashover, but also the electricity pass through can damage the internal tissues, veins, and all those things also. So that is a potential danger with electrical shock plus arc flash. And the other thing is that in an arc flash, if you get a 3rd-degree burn, actually, basically, your inner skin is completely burned off, and it's very difficult to patch up that. You need to skin graft and all those things. It's like a cooked meat, right? So that's it. That's a reality. Yeah.
Okay. So the severe when it comes to severity, the injury from arc flash is so high, right?
Very high. 3rd-degree burns, mostly 3rd-degree. Yeah. Yeah.
Thank you, Jobi. Thank you, Nanda.
Right. Thank you very much. There are no more questions. We move to the formal closure of the session. Mr. Jobi, a wonderful presentation. I agree with all other participants' voice. It was a very extensive one. I could understand when you said the time was a limitation. Yet you covered very excellently with nicely interspersed videos. I think it made very interesting subject. Covering
I think Raju has some questions, right? So,
yes,
yeah.
Raju, over to you. Raju is your classmate also, I believe. Raju Mohan,
Yeah.
It was an excellent presentation, Jobi.
Thank you, Raju.
It was very enlightening because most of them were real life scenarios. You say a picture can speak 1,000 words, but those videos could speak 1,000,000 words. So thank you once again from all of us.
Thank you, Rajmohan. So once again, thank you, Mr. Jobi, on behalf of HSC Forum, National Safety Council Kerala chapter, and Department of Electrical Inspectorate. I extend a very formal warm thanks to Mr. Jobi Jacob for his wonderful presentation today, covering extensively on the electrical safety requirements as far as the arc flash is concerned, the mitigation strategies. I could understand a lot many more on what electrical arc flash requirements are, and also I think the awareness is a lot more needs to be done when working on electrical circuit. While we are talking extensively about electrical shock, I think electrical arc flash risks is not discussed so much, and also the need to wear the PPEs, especially while working on the arc flash boundary areas where people are exposed to. You covered extensively on the what is the restricted space, limited space, and arc flash boundaries. I think when working on that, the need for PPE, the tested PPs, which can withstand those kind of situations, need to test the switch gears, they're designing the switch gears to kind of withstand those resistant designs of arc, where to stand, where not to stand when you are energizing. A lot of meaning, and also the nice arc flash matrix. The PP matrix normally I've seen, but arc flash matrix was quite interesting. The relevant standards were also covered. IEC Open Arc Testing Standards, IEC 61482, 1 and 2002. So thank you very much, Jobi, for the great enlightening session. Also thank all the participants who were present here for this safety webinar. Wishing all of you a happy weekend, and let's all together work to make electricity quite our slave, not the master, and use it very safely and responsibly. Thank you all once again, and thanks to Jobi once again. We've now formally closed the session. Thank you very much.
Thank you. Thank you.